Picture a time before Earth, before any planets, just a vast cold cloud of gas and dust in the Milky Way. A nearby supernova sent a shockwave through this cloud, triggering its collapse. Gravity pulled the material inward, spinning it into a giant disk. At the center, a dense ball of hydrogen and helium formed a protostar, our Sun, in its infancy. For millions of years it grew hotter and denser, gathering mass from the disk. The first giant planets like Jupiter and Saturn began to form in the swirling material. After about 50 million years, the core of the protostar reached the critical temperature for nuclear fusion. Hydrogen atoms fused into helium, unleashing a wave of energy. Outward pressure balanced gravity, and the Sun burst into light for the first time. The solar system was illuminated, a new star had been born. The stage was set for the story of our Sun and its planets. With nuclear fusion ignited, the Sun entered its main sequence, the stable, middle-aged phase it's in today. Gravity tries to crush the Sun, but fusion pushes outward, creating a perfect balance. Every second, the Sun converts millions of tons of hydrogen into helium, releasing immense energy. This steady output powers life on Earth, drives our weather, and makes our planet habitable. The Sun is just the right size for life to thrive, neither too big nor too small. It's an average star, but vast enough to fit over 1 million Earths inside. For billions of years it's been a reliable engine of creation, orbiting the Milky Way. But even this golden age won't last forever. The Sun is slowly changing, growing brighter as it ages. Its core builds up helium, increasing pressure and temperature, making fusion run faster. Every 100 million years the Sun's brightness increases by about 1%. In 1 billion years it will be 10% brighter, triggering a runaway greenhouse effect on Earth. Oceans will boil away and Earth will become a scorched, lifeless rock. As Earth dies, moons like Europa and Titan may briefly become habitable. The habitable zone will drift outward, but the Sun's life-giving phase is temporary. The Sun's evolution is a reminder, even stars have lifespans. In about 5 billion years, the Sun will run out of hydrogen in its core. Gravity will collapse the core, igniting a shell of hydrogen around it. The Sun's outer layers will swell, transforming it into a red giant. It will expand, engulfing Mercury and Venus and possibly Earth. Even if Earth escapes, it will be scorched and lifeless. The Sun will fill the sky, a fiery spectacle hundreds of times larger than today. Deep inside, helium fusion will ignite in a dramatic helium flash. But this new fuel won't last long. Helium burns quickly. The Sun will shed its outer layers, marking the beginning of its final act. The red giant phase is both magnificent and destructive. After its red giant phase, the Sun will shed its outer layers, creating a glowing planetary nebula. At the center, the Sun's core will remain, a white dwarf, Earth-size but incredibly dense. This white dwarf will no longer fuse elements. It will simply cool and fade. The nebula will disperse, seeding the galaxy with elements for new stars and planets. The white dwarf will radiate its remaining heat for billions of years, growing dimmer and colder. Eventually it will become a black dwarf, a cold, dark remnant drifting through space. This is the Sun's final fate, from a brilliant creator to a silent relic. The Sun's story is a cosmic cycle of birth, life, and quiet death.